Hello, everyone, and welcome to this fourth session of Entanglement, Physics, Mind, and Worlds. I'm James B. Barbieri, Program Coordinator here at the Power Center, and I will be your host for today. As a host, I'm here to help you, so any problems, please let me know in the chat. Just a quick reminder to please mute your microphone, and we do encourage you to turn on your cameras. Feel free to use the chat to talk to all the other participants throughout the call. And we do also have closed captions available if it's easier for you. Also, this session is recorded for archival purposes, and for you all, you should get the recording in a couple of days. So today we have the honor of having our good friend Basil Hiley with us. Basil is a British quantum physicist and professor emeritus of the University of London. He received the Majorana Prize Best Person in Physics in 2012. He was a longtime co-worker of David Bohm, and he's known for his work with the implicate order and his work with algebraic descriptions of quantum physics in terms of underlying symplectic and orthogonal Clifford algebras. Hiley co-authored the book The Undivided Universe with David Bohm, which is considered the main reference for Bohm's interpretation of quantum theory. Today, he will be talking with his session entitled My Entanglement with Entanglement. With that, I'll pass it over to you, Basil. Welcome.
Thank you very much, James, and hello, everybody. We've been having a great fun before we opened up to everybody else, so I'll try and calm down and get on with some serious stuff rather than what we were talking about. I thought of this session, I would actually talk about my experience with entanglement rather than giving you a description of what it's all about, because I think you've had some very good courses from Jonathan, from Jose, and from Emily already, dealing with what I would call the standard stuff. What I want to talk about is the not so standard stuff that I was working with David Bohm. I mean, I started out after getting a PhD in solid state physics and had an amazing opportunity of working with David Bohm. He got the chair of physics at Birkbeck College, and I was able to convince them, con them, that I could help him in quantum mechanics when I really knew nothing about quantum mechanics at that stage. And I was very fortunate because at the same time, there was Roger Penrose in the maths department. And that was a very nice department. It wasn't very big, and it was before Roger was famous. Bohm, of course, was infamous at that time, but it was great fun having seminars every other week, I think it was, during term time, while I was desperately learning to catch up with what the two greats were talking about. So that's really where my story begins, but I want to go further back than that. Can I share the screen? Good.
Yeah, you'll be able to.
And now we should have done this before rather than me telling jokes. No, it's the wrong one. Sorry about this, folks. Okay.
That's it. Yeah.
I think we're up and going now, aren't we?
That's
Yeah.
good.
Oh, yeah, okay. So here's my first slide. I was very happy to find that Anthony Gormley had been listening to a discussion with David, Pete, and myself. Great center that David started up there in Paring. And this is what resulted from it. Anthony had been rather interested in what we've been saying about how we abstract matter from a relationship structure, and he managed to think about this in a really big scale. And this is actually on the banks of the River Thames. I've not seen it myself, but I've actually seen it in many different photographs. It's a magnificent picture, if you like, of what it was that we were trying to do in those early days with David and Roger. And my entanglement started fairly early on, and I sort of put this in as a humor because you got a nice picture on one side and you've got a mess on the other side. And the question is, how do you untangle that? And there's more in it than probably I'll be able to talk about. And that is that knots plays a very important role recently in my work. So I've linked up with Lou Kaufman in what he is doing, and we find we are sharing common ideas. But now, the first thing I've got to say is that I am not a supporter of Bohmian mechanics. And a lot of people think, oh, you're a Bohmian, and immediately think Bohmian mechanics. But Bohmian mechanics is not what we were doing. It was rejected in David Bohm's book on causality and chance. But it's a nice, simple, and I'm going to upset people by saying it's a nice, simple Mickey Mouse model of what David was really trying to think about in those early days. And I want to go right back, in fact, to entanglement. I just wanted to put that slide in there to make it clear. I'm not talking about Bohmian mechanics at all. In fact, I'm talking about Bohmian non-mechanics. In David's quantum theory book, the textbook he wrote in 1951, I think it was, in there he actually says that calling it quantum mechanics was a misnomer and it should be called quantum non-mechanics. Okay, having set that aside, now entanglement. So as I put here, it all kicks off in 1935, because that's when I entered the world screaming, no doubt.
Well, I'm sorry to interrupt you. I'm not sure the slides are advancing. Have you moved on a slide?
Oh, aren't they advancing? Yes, I have. Oh, golly. Okay, can you hold on a minute? I know what has to be done.
On the screen I can see is still the quantum cloud.
Right, okay. Can you just wait a minute while it's winding up? I thought I'd get away with it without doing that. You see, James, you shouldn't have encouraged me when I joined you earlier on.
It was Jenna's fault.
I apologize. That's on me. That's on me.
No, I don't know. I don't want to blame the ladies. I want to blame James.
Oh, good, good, good.
Know all the gossip.
Yeah. Only I should have been doing this right now. Can you see me now?
We can still see starting slideshow.
You're not seeing me?
We're not seeing the slides.
You
No.
know what might be a good idea? Stop sharing your screen and then come back in again. That might make it a little smoother.
Stop sharing.
Yeah.
Okay.
And now try again.
Come back sharing. Can you see me now?
Yes.
Okay, so what am I going to do? Play Keynote live?
Yeah.
Right. And then it's going to wind up again. Oh, good. That's come up very quickly. Can you see it now?
No.
No.
I think it's playing on the Mac rather than Keynote.
That's not going?
No.
Okay.
All we
nobody.
see is, yeah, we just see starting slideshow and it doesn't let us actually see anything.
Oh,
Maybe if you start the slideshow and then share screen, it might work.
That's a good idea. Well done, Mark. Yeah.
You're muted now, Basil.
Basil, you're muted, so we can't hear you.
yes, I can. Okay, now what was I supposed to do?
Start
Trip
the
down.
show and then start sharing.
Start sharing. What I'm going to do is to share. Oh, I wonder if, hang on a minute.
I think if you start the slideshow, Basil, first, and then
Okay.
share your screen.
Thank you.
Get it
That's
up and running first, and then try and share.
Okay, I'll get it up and running. No, that won't work. Sorry, folks.
What
Can
you
you-
could do is just go back to the editing screen and just click through it slide by slide on that.
Yes, I'm going to do that, which I don't really like doing, but that's
No,
going to work.
I understand. Yeah, but it's a quick answer, I think.
Yeah, let's go that way. So if I just get hold of you. Now I've lost the Zoom. There's the Zoom. Okay. There's my master slide.
Yeah.
Can you see it?
Yeah.
That's fine.
Shall I try playing now?
I personally, I'd just click through the slides if I was
Oh,
you.
okay. Yeah, but this is going to be the trouble. All right. Now, so I've got to start again. I'm sorry about this, folks. There's the quantum cloud, which I've talked about. Then I wanted to show this caricature here of my struggles with trying to understand non-locality, entanglement in particular. And I made comments about the knot, and there you can see there's a tangle there. It's full of knots, and you have to untangle it. Then I wanted to confirm that I was not a Bohmian mechanic. So I used this slide showing that it's not for us. It's a very mechanical picture of what David Bohm originally intended. And he intended something much more subtle than that. And then we've seen the Einstein-Podolsky-Rosen description. We've seen how Schrödinger came in with entanglement. And there, the words that we were interested in was Verschrecken. I remember Jose said, could anybody pronounce it? Here is the verb verschreck. And it's translated as entangle, entrap, ensnare, tangle, mix up. But there's another word very closely, a German word closely related to it, verwickel, and that is involve, engage, entangle, and implicate, which I thought was rather an interesting definition that I found in Google, of course. Now, what I want to draw attention to is Bohr's response. Remember, Einstein raised this objection, and then Bohr answered it in the same year. And the answer was, from our point of view, we now see that the wording of the above mentioned criteria of physical reality proposed by EPR contains an ambiguity as regards the meaning of the expression without in any way disturbing the system. Of course, there is no question of a mechanical disturbance of the system, no way of a mechanical disturbance during the last critical stage of the measuring procedure. But even at this stage, there is essential question of an influence on the very conditions which define the possible types of predictions regarding the future behavior of the system. Very curious word, influence. If influence is not a mechanical force, whatever is it? I remember talking this over with John Bell, and he agreed. It was almost totally meaningless. Nowhere in Bohr's literature can I find anything other than a re-expression using the words influence. Okay. So now let's have a look. Let's go back to quantum mechanics, that we've seen some of these things. And remember, it essentially started with particles coming into a two-slit system, and we're seeing interference patterns. And that shouldn't be a particle. A particle shouldn't do that. A particle should do this here, which is called a ropey machine gun. I call it Bohr's ropey machine gun, which fires at random into the two slits, and you find that you just get a pile of bullets like that. Whereas if you use the a wave, so we've got a liquid here, we excite some waves in it, pass them through the two slits, and what we see is this pattern. And when we do the same thing with electrons coming out of this little device here, what we find is not the particle picture, but the wave picture. And then the question was, what are the waves? And the early photographs, I think we've seen these already, is that as time goes on and you let them in one at a time, you slowly get an interference pattern building up. So the interference pattern is the arrivals. And then because it's so difficult, what the heck is happening between the source and the screen? Well, let's just describe it by means of a wave. And so then that's the way wave mechanics began. So you associate a wave with the particle, and that's where all the problems start. Now, we were fortunate in obtaining some money to do weak values, to measure weak values. And so we had to get down to first principles. And what we did was to build up this machine here. And this is trying to find the fringes using argon. And the two main culprits behind this setup was Joel Morley and Peter, oh God, I forget it, another Peter, I can't remember his name, I'm sorry. And you'll notice two interlopers in the background there. We're theoreticians who shouldn't be in there. And then at the end of this tube here, so we get the excited atoms up here, let them go, and because they're excited, they're very hot and they're jumping around all over the place. We've got to cool them down. And so we've got a Zeeman cooler here, and then we eventually trap them in the science chamber here. Don't know whether you can see the sort of a little glow in there. Well, we took a photograph. Mobile phones are absolutely beautiful. You can take a photograph, and that's the ions which we have trapped in that container there. Because all of this is in a vacuum, very high vacuum. So now what we've got is the screen. So let's see what happens. Just to make sure, you see, that we can control that ball of argon atoms so that we can slowly move them backwards and forward. This is all done with mirrors, actually. It's all smoke and mirrors, you realize. It's all done with laser tweezers. And then what we want to do is to drop them into the container just on the bottom here. That's where all our detecting equipment is at. And then we see the following picture. So we have actually produced the fringe patterns in our own laboratory down in UCL in London. And you've seen a lot of people have done this now, but we had to make sure that if we're really dealing with quantum mechanical objects in a quantum mechanical way, we ought to be able to reproduce the fringes. So whatever we're doing, we're getting quantum mechanics. Okay, so that's a bit of the background of how you see these things. Now come into the theory. And this was the original Bohm theory. And I'm trying to make it very simple because I know people don't like mathematics. But we said it's a wave. We've got to describe the particle by a wave. Without wondering what that means, we're just going to predict the results. And the wave is in terms of an amplitude and a phase. And what we find, if we put this into Schrödinger's equation and just look at the real part of the Schrödinger equation that results, we get an equation which looks like that. Doesn't matter about the form of it. I want you to compare it with the classical way of describing particles following trajectories. Now it looks, the form of them is exactly the same, but there's a gap here. So my first insight was, well, or David led us to this insight, maybe that the difference is summarized in that term Q, the quantum potential. And it's an energy, so I'd rather call it a quantum potential energy, because that equation, either that one or that one, is simply a generalized conservation of energy. So we're saying energy, the total energy, is the sum of the kinetic energy, the classical potential energy, and this additional energy. And that term was causing a lot of problems. A lot of people say it doesn't exist. In fact, it does. It appears when you know where to look for it, almost everywhere. I came across it in a paper by Bryce DeWitt in just last summer before last, and I found that he had got it in there and he called it the quantum potential. Now, Bryce DeWitt worked with John Wheeler and that very fruitful cosmological school in America, in Princeton. And Bryce is a tremendous mathematician, and he actually called this the quantum potential energy. It appears in wave theories of classical waves. And in fact, I found it in a paper in 2013 that is written by Michael Berry. And he talks about the quantum potential. So it certainly is around, it's everywhere, if you know where to look for it. So what does it look like? Well, first of all, because of the way we have constructed the relationship between the momentum and the phase and the energy and the phase by that differential equation, we can solve the differential equation, and we see that the particles, if they are particles, are following trajectory according to the mathematics. Please note, this is a mathematical simulation. And we can even have a picture of the quantum potential. This is a time average picture of it. The atoms are coming in here with this. We've replaced this with Gaussian slits rather than hard slits because it's much easier to do the numerical calculations with Gaussian slits. And look at this extraordinary picture. And then, of course, we can have a look at a wave packet, because one can quite easily think that maybe the particle is really replaced by a wave packet. And therefore, we want to see what happens as the wave packet comes in to a barrier. Remember this game, you're playing quantum tennis, hitting your ball against the brick wall, and depending upon how hard you hit it, it actually goes through the brick wall and appears on the other side. That's radioactivity. Okay, so now can we simulate that picture? The answer is yes. And these are the centers of the wave packet, or the trajectories that are calculated from the wave packet. And the center of the wave packet is about here, I think. Where's I can't see properly. It's about 50. If you can, I don't think you can see it with this magnification. It's probably about here somewhere. So it's only the ones at the front of the wave packet that actually eventually find themselves leaking through the barrier. But notice there's also some remaining in the barrier. And if we look at the quantum potential, we can see a correspondence between the wave picture there and the quantum potential. And we see these beautiful patterns here. So what on earth is going on? What on earth is going on? Sorry, I went the wrong way. Okay. So let's see. So that's just quantum mechanics. And then in this topic here, we're talking about entangled. What we can do is we can take the wave function of the two particles, particle 1 and particle 2, at the same time t, play the same game, only now the amplitude and the phase are more complicated, put it into Schrodinger's equation, and what do we find? The kinetic energy of particle 1, the kinetic energy of particle 2, the quantum potential energy, and the classical potential energy. And the quantum potential is just more complicated, but the principle is there's a new quality of energy in this picture floating around somewhere. Because if we put that classical potential equal to 0, the particles are still locked together no matter how far they are separated. Because that's a common time. Okay, and what's more, that energy term does not necessarily vanish as the distance between the two particles increases to infinity. That is really incredible. They're somehow together, yet they're apart. And of course, there are lots of jokes made on that kind of idea. Okay, look, this is mathematical equations again. Come on, BJ, give us some pictures. And here are the pictures. What we've got here is particle 1, and this is particle 2. And here I'm using the idea of spin, which fortunately Jonathan and Jose have already talked about. And the wave function that is entangled is that particular object there. And this is just symbolic. That's the wave function for spin up. That's the wave function for spin down on particle 2. Wave spin down on particle 1, spin up on particle 2. Just read it like that. That's just a way to read it rather than in words. Now, what you do is when you've got a particle with spin, when it goes into a magnetic field, it actually interacts with the magnetic field, and you can decide whether the particle is up or down by having a Stern-Gerlach magnet, which is this thing here. It doesn't matter what it looks like. We'll see one later on. I realize I should have put it in earlier. But what you find then on the Bohm calculations, on the simulations, that the particles that are in the top of the beam, they're coming in from here, going this way, the other one's going that way. So they're coming in here, this particle 1 comes in here, sees the magnetic field, and starts responding depending upon what its initial condition is. So if it comes in here, it goes up pretty quickly. If it is here, it goes up rather more slowly. And if it's here, it comes down And if it's here, it's down. And if it's here, it's down. But look what's happening to the particle at the other end. And this might be on Mars, miles away from your Stern-Gerlach magnet. As this is reacting here, that locking together of the two particles through conservation of energy is beginning to turn in the opposite direction. So this tells us there's nothing there to begin with, that the total spin, the mean spin is zero, but somehow they're coupled together. And this is the mystery. But the explanation in this simulation is the appearance of this quantum potential term. Now, the reason why Chris Dewdney could do these calculations was because he already knew that Bohm had already shown how to get spin into the story. And I'm not going into that because it's a bit hair-raising. And but it can be done. It was done in 1955 by Bohm, Schiller, and Tiomno. That's when Bohm was in exile in Brazil. And it brings out very clearly non-locality. Now, it's also been tested to 143 kilometers. That's when the world record. But now I've been told that the Chinese, the people from Singapore, I think Yosei was telling us about this, that they are getting entanglement between the Earth and a satellite. Quite extraordinary. Okay, where do I come into this story? Because it's supposed to be my entanglement. Well, oh, I did this. Sorry, I went one slide too soon. I'll tell you my story in a minute. But for those people who want to know how to see this thing in a much better picture nowadays, by my very good friend Peter Van Rieth at UCL, we can now do color simulations. Whether it helps or not, I don't know, but it's certainly more pleasant on the eye. And I thought I'd just put in what the quantum potential looked like for a spinning particle to show that you can calculate it. That's the ordinary translational part of it. It's split into two parts when you go into the Pauli equation. It's got a transverse part and a spin part, a translational part and a spin part. And the spin part is the angles, just as if it's a spinning top. Now we're told the spinning top is not the right model, but remember, this is simulations, and a lot of physics is doing things which are not quite right, and then seeing why certain effects are taking place, and then scratching our heads and trying to work out what is actually going on. Here is the Stern-Gerlach magnet I was telling you about. It's got an inhomogeneous magnetic field, and that enables us to split the spin systems. But look at this, what's happening here. The magnetic field stops there in the simulation. And yet, out here, there should be nothing. But the spins are still going, and the spins are still turning. And there's no known field except the quantum potential energy out there. There's that coupling term. And finally, you find that the beam, so there's no jumping into an eigenstate, as there's no Schrödinger jumps. In this model, there's a smooth transition into the up state and the down state. The up state is up here, the down state is down here. Now, people say, oh, well, you only had, this is all non-relativistic, and surely you can't do it for relativity. Sorry, folks, all those people who are pinning their hopes on that, you can do it. And in fact, I've done it with Bob Callaghan, and also there's a school in Brazil, Rodrigues Jr., as he was, I can't pronounce his first name, I'm sorry. Unfortunately, he's no longer with us, but he has actually done the calculation in a different way from the way I did it, but got exactly the same results. And I'm therefore happy that I've not made any mistakes in what I've done. And what you find is the quantum potential for the Dirac particle, so this is fully relativistic, is something which looks like that. That's the translational part. This is the angular part. And if you compare it with the Pauli, this is the sorry, I'm getting all flustered here. The translational part, and this is the spin part. And then the ordinary Schrödinger equation, where we've done all our thinking about, it's just that term there, and that term emerges from that term, and that term emerges from that term. So there is a consistent going from the relativistic to the non-relativistic. Okay. So do we see these states in physics? Well, nowadays, of course, we did. But when I was going into that, it was not, non-locality was not mentioned. Please leave the room. If you talked about entanglement, you were supposed to leave the room. And I remember being interviewed by Paul Davies for his program, which he had on the BBC. And he said to me privately, he said, of course, we know the world is not non-local. So I was in that era. Nowadays, it's almost accepted. But in those days, you looked for where are there entangled states? And you find there are entangled states in the strongest chemical covalent bonds. The two electrons from neighboring molecules exchange each other, get involved in a tussle, get involved in an entangled state, and that gives you a very strong coupling. Again, helium, if you look at helium, it has 2 electrons in the shell, electron shell, and they are in an entangled state. So the question really was, in those days, does entanglement survive macroscopic distances? Now, we could tell that without, this is before Bell's inequality, by the way, just to get the record right for the history. And we said, well, there's a very simple way of disentangling them, that the wave function this becomes a product wave function, and then the 2 particles are completely separate. And that was called the Furry state. Now here, the entangled state, not separable, but the Furry state is separable. And therefore our idea, or the idea of David Butt, a reader, and Alan Wilson, was to see if we can have an experiment where they were dealing with beta decays and they knew about positronium. So they were looking at a positronium atom splintering, annihilating into 2 photons, which go in opposite directions with opposite spin correlations. And how do we do that? Well, we measure the spin correlation, and they actually give us different results. There's the entangled result, and there's the unentangled result, 2 independent particles. And we've put in, I call a uniform, there we average over all spins in that case. Okay, so what we were looking at was there such a thing, a new process called spontaneous localization? Now that might seem far-fetched. What the devil are you talking about? Well, this came up while we were doing this experiment when Hawking introduced the idea of black hole radiation, and suggested that there would be many mini black holes floating around the universe. And this is a beautiful way of measuring those the density of those mini black holes, because that's where the non-unitary transformation in going from here to here could take place. And I think we did a calculation and found that there were 1 in 10 to the minus 50 mini black holes in our experimental results. Okay, so what was our experiment? Or what was the experiment that Wilson and Butt and June Lowe did? I put them in that order because this is really something tragic happened here. And this is why we, as it were, got left behind, if that's the way you want to put it. Alan Wilson was a young physicist who joined us at Birkbeck and was beginning to make a name for himself. But he loved climbing. And every weekend, as far as I could gather, he would get in his clapped out old Mini and drive to where there was some rock to climb. And one particular weekend, he decided to go to Great Gable in the Peak District, I think it is. And unfortunately, you can tell what I'm going to say, he fell and he killed and he died. And he, unfortunately, the experiment had to be postponed for a bit and we had to find someone new, and that's where June came in. And Butt was really the guy who was the chief supervisor. Remember, the supervisors never do any work. They always get their research students to do all the work for them. So once you're, but Alan had to do some work because he was trying to get himself established. And so he was being the dog's body and doing the actual experiment. Okay, so what's the experiment? Oh, and the other thing was we got it all set up in the laboratory, in a lecture theatre, which we were allowed to use in Birkbeck. And then it was an arts faculty lecture room. And then the arts faculty said, oh, come on, you can't use that room anymore. Would you please move your experiment somewhere else? So we had to take all the pieces, take it down 3 flights of stairs and put it where all physics is done in the UK, in a basement in those days, in a basement. Okay, so here's our positronium source and the 2 photons, one goes there, the other one goes there, and you measure their spin polarization by means of these boxes here and there. If anybody's interested, you can see to move the thing across, all you got to do is to have a mouse which is not working properly. And but in this experiment, it's actually, they put the detectors so they could move them further and further away on wheels. So we had these 2 trolleys and they would move them further and further apart, taking their measurement results. You then look at the correlation and you're looking for something which is going to dip down. Remember, it's either cos theta or a third of cos theta. So by the time they are separated, so that they are space-like separated, and the wave functions no longer overlap to have any covalent type argument to keep them together. We finally got out to 5 meters, which satisfied, so that would be 2.5 meters, that would be 2.5 meters, and that would be 2.5 meters. And that was sufficient to satisfy all these criteria. Now, while we were doing this, Jean-Pierre Vigier came from France and asked, why are you moving it so far apart? And I said, space-like separated. Your detectors events have to be in a window which makes sure there's no naughty conspiracy between the detectors signaling each other, please get in this position or get in that position. So to rule that out, they must be space-like separated. And then I think Vigier went back to Paris, and the story I got told, I don't know how true this is, that Aspect immediately started moving his detectors further apart. But I won't go into that story here. Now then, I'm going to do something new now. Shall we have a break here, James?
We can do if you want. Yeah. Should we take 5
I
minutes?
mean, I know it's a bit early, but I think this might be a time to have a break.
No,
Just 10 minutes, okay?
10 minutes. Okay, let's come back at, well, 3 minutes to the hour.
Yes. Yeah. Well, yes, just after 5. Yeah, just after 5 to 5:55.
Yeah. Okay, no problem. See you all in 5 minutes.
Yep. Okay. Well, Eleanor, I'm sorry, are you there?
We are.
Yeah, no, I'm sorry. You see what happens when we don't get on and do the proper business?
Well, it was a lot more interesting what was going on in the waiting room than the slides. So you're good. It was fine.
Okay, well, I'm sorry. I hope the other people who are listening in didn't get too put off by that.
No, it was wonderful.
No.
Have you got a cup of tea with you there?
No, I don't need a cup of tea. I can still, I'll get my water bottle. You see, I've got my.
Nice. I'm going to should I resist the urge to ask if you have any electricity?
Oh, okay. Sorry.
Ah, look at him. Look at him.
Sorry, I didn't even realize I'm looking at the screen and the screen is bright. And now I look outside and I realize that, you know, we've gone past light up time.
Yeah.
But there you are. Thank you for reminding me to switch it on. The rest of the room is still dark. Actually, I think my face is a different color when you switch the light on. To me, it looked bluish, but now it's looking more like it's.
It looks like you've been to Spain.
Yeah.
Yeah. Well, it may be. I darken very quickly.
Really?
Yeah. And I wonder if that's something to do with the family history of being in the Far East. That my father was in the Far East. His father was in the Far East. My mother's father was in the Far East.
Basil, are you in London now?
Yes, I'm in London now.
Right, because I'm traveling, but I'm in London again. So I wondered if I was next door to you. I don't know whereabouts you live in London.
Well, where are you on the train?
In Kensington.
In Kensington. No. Yeah. Oh no. You live in posh places.
No. I live in Wanstead, but I'm visiting friends in Kensington.
Okay. Well, I live in Croydon.
Oh right. Yeah.
For those who know about the UK, Croydon is a dump. The council have gone bankrupt twice, and we've got to pay a hefty rates bill to dig them out of their problem, which is a bit annoying. There'll be some trouble in Croydon before long.
You'll have to move to Paris.
Yes.
Yeah.
How
We'll
are
all
you?
have to move to Paris.
Yeah, everybody should.
Yeah.
How
Yeah,
are
but
you,
the trouble,
Bernard?
but the
How are
trouble
you?
is they won't let me in again because of Brexit. I could travel to Paris without even batting an eyelid, and now these stupid people. I'm sorry.
You just need a passport. I mean,
No, you wait. Passport. You wait till the visas come in. You wait.
oh gosh, don't. Oh
You
no.
wait. You wait.
Was it a boat?
A boat. We'll come pick you up on a boat. Yeah.
Yeah, okay. I've got a rubber dinghy somewhere.
But Basil, you're British. You don't need a visa to go to.
Oh, yeah, but
you-
look where I was born, Jonathan.
No, it's Bernard Carr.
It's
Oh, it's
Bernard
Bernard.
here.
Sorry, Bernard. Sorry, Bernard. I thought I missed. I'm going deaf as well.
No, because you wouldn't know, because the name is wrong from the on the base of the image.
Okay. No, but now I recognize the voice. No, I once said when they were having all this passport row about whether to let Ugandans and who knows who else into the country. And I said, but look, I'm born in Burma. Will that make me a British citizen? Oh, don't worry about that. You're white. Sorry, those are the actual words that the clerk used.
I didn't know you were born in Burma.
Yep.
I think Croydon might be better than Burma now.
Oh, definitely.
Yeah.
Definitely. I never had a chance to go back to Burma. I was going back because I found myself in Borneo, would you believe it? And I went to Thailand, and I was going to go in to Burma via Thailand. It's much easier to get in that way than to get this way. It was in those days. Don't forget, I'm talking about history. But unfortunately, this is when the army had taken over and shot a few thousand students. And they weren't advised, they'd advised that it's not safe to go into Burma. So I had not to go into Burma. So I've never been back. So they sing about the road to Mandalay, and I traveled the road to Mandalay, but unconsciously as a kiddie.
But you are British, aren't you?
Yes, I am.
Yeah.
They finally gave me full British citizenship, yes. But a lot of people in those days in the in the colony would actually send their wives home to be born in the UK so that they would be bona fide UK citizens. There was always that feeling that, you had to be born in the country of which you're a citizen. Never quite understood that, and I think that's all gone out of the window now, has it? I don't know. What happens if you're born in your country in which your parents don't have a passport?
Well, you don't, it depends on the country. In England, you don't get one. You'd have to apply for it later on.
Oh, I see. So automatically you don't become English by...
No, James was born in England and is not British.
Oh, okay.
Yeah, there's a perfect example.
Look at him. Look at him. You can see it all over his face.
Yeah. But don't worry, we'll come and rescue you if anything. Although I don't think you want to come to the UK anymore at the moment. It's a bit grim.
In Britain, you have to be very careful now not to say, where do you come from?
Oh, yes.
A case recently where one of the ladies in waiting asked one of the ladies, who I think was from Ghana, where you come from, and she said, from Britain. And she said, no, but where do you really come from? And this caused great offense, so she had to resign. But
yes, well, I got caught out on that earlier on, because I'd see an Indian face speaking fluent, and I would say, where do you come from? And usually they say Watford.
yeah.
And then I suddenly realized, because I was trying to make a link so that I could talk about where they came from.
I think it's all to do with the fact that we all inhabit multiple localities at the same time.
Yes.
Subjectively, and objectively, and politically, and sociologically, and psychologically, all at once.
We're entangled.
Yes,
we're entangled. Well, Jen, yeah, that's the whole point about the entanglement. Anyway, so I hope this way of presenting things is not spoiling it too much. It's not a nice polished way.
Not at all. It's good. Could I just take you back a couple of slides, though? Don't actually go back the slides. Can I just ask a question going back? Which I ask it because it might be, the answer might clarify things for some of the audience. On a couple of slides back, you mentioned Dirac particles, Pauli particles, and Schrödinger particles.
Yeah, well, that's the slide here.
Yeah. Could you just very quickly give us an idea what the difference between them is?
Well, how do we do the Schrödinger particle? We write the wave function as R e to the is, and then separate real and imaginary. Okay, simple for those who are. Right, now then, when we look at the Pauli, we actually have a matrix already for the wave function. We have R1 e to the S1, and underneath that we have R2 e to the S2. How on earth do we combine those two imaginary numbers? You can't do it that way. You've got to be a little bit clever. And the clever is going to the Clifford algebra.
So you're saying a Pauli particle is a non-relativistic spin half particle?
Yes.
Right, cool. And so a Dirac particle is a relativistic spin half particle?
That's right, yes.
Cool, got you. Thank you.
Yeah. And just to notice that spin is not something quantum mechanical. It's to do with the properties of space. And that is what Clifford did in 1885. You derived the wave function for a spinning particle without realizing he'd done it. The Clifford algebras contain all these properties. As you go up, you have a tower of Clifford algebras, starting with the complex numbers, going up to the Pauli spinners, the Dirac spinners, the Penrose twisters, and above. There's one layer above, which I don't venture into, except I've been forced to just recently. All of those were discovered by Clifford. They're in Clifford's algebra. And all he was doing was trying to tell people how to get to the George.
Basil, can I ask you a question
Yes.
About something? I mean, one always says that spin in quantum mechanics does not actually correspond to spin. It's something more abstract. However, I've always, and I said this to Jonathan actually when he gave his talk, to me, it's always interesting that if you think it really is spin, then the quantum wavelength tells you that the rotation speed at the surface is the speed of light.
Yes.
And I've always thought, well, that's actually an argument that it really is. The quantum wavelength actually is telling you it really is a sort of spin, because it's telling you this. But
sorry,
so,
I'm interrupting again. I always interrupt. I'm sorry, Bernard.
No, that's fine. I was going to ask if you believe that argument, because and how it relates to these more sophisticated language of Clifford. And
yeah, I knew you were going to ask me that. That's why I stopped you before you did. and suggest that you should look into that and see if you can find the answer to it. I don't know the answer.
Oh, okay. But it's people always say it really isn't spin, and it seems to me that it really could be a spin.
Well, I've got a young man working on a PhD thesis who's saying it's not a spin, it's an algebraic element, and I'm going to try and move on to that now.
Yep.
And I know, James, can we start?
Of course, yes, we're on the hour, so teasing made.
Right. So now is going to be a completely different story. I'm now going to do not standard quantum mechanics, but the Bohm Hiley. I'd try to leave David out just in case, because Dave never saw this. This came from discussions with him. I'll call it the Hiley story. And then if it's rubbish, you can blame me for it all. What is, we keep hearing, or at least we used to keep hearing this, it's non-commutativity, it's non-commutative geometry. What is this non-commutativity? Is it something magical? Not really. It's something that we grow up knowing. Suppose we take a book and rotate it first around the z-axis and then around the x-axis, and we get the configuration which looks like that. Now let's do it in the opposite order. We do the x rotation, we do the z rotation, and they're different images. And in fact, this can be the notation that I think Jonathan and Jose used, was this symbolism here, but this is just a place to put the book, if you like. So what are you going to do to the book? You're going to rotate it. So then you operate on it and you rotate it. Then you rotate the rotation again by X. And what happens is you produce a different symbol here. This is I wanted to draw the boxes in here, but I didn't have time because I've only just made this slide up this morning. So the outcome is not the same, and that's what we mean by non-commutativity that we all know and love. But this is passive non-locality, passive rotations. We're actually doing it to the book. The real interest is what happens if the process is an active process, that you are actually doing it. Then you can sort of feel it. And remember, David was very interested in this running across the stepping stones in the biography that David Peat wrote, saying that was the movement, it was one whole. So what does it feel like actively to rotate? Okay, well, before you do that, I can tell you that if you try walking through a door before opening it, you will certainly experience it. But if you want to experience the rotation, well, you can go on a centrifuge, but you don't really need to do that expensive stuff. You can actually take your kiddie to the roundabout in the park and you watch the kiddie. If he hasn't experienced rotations before, he runs with his translational energy, jumps on the roundabout, and suddenly you have to pick up a crying baby with scrapes and goodness knows what else. The experience of on the roundabout is very different from the translational experience. So if we were thinking of process as active, somehow the translations and rotations have to be thought of as the particle actually doing this, or the particle is a flow of energy rather than the particle is a billiard ball. So we're thinking about the fundamental elements of nature are process, not particles. And I've mentioned Coriolis force there, but that's for another lecture. Okay, so let's have a look at active. The other day I was listening to Roger Penrose and he was talking about googly problem in twistor theory. I'm sorry for the people who don't understand cricket. We British have left cricket all over the Far East and they are now coming back and showing us how to really play the game. But why cricket? Oh, just because it's a nice, simple thing. I want to play quantum cricket. Now, if you play cricket, you've got to have a ball and it's got to be red. Tradition. Okay, but suppose you've got a bundle of objects that someone's just thrown out of his carts and says, go and pick out of that a series of red balls. Now, in this universe, you can't see that unless you put glasses on. It's a bit like me now, you've got to put glasses on to see. But these are special glasses, and that is the colored spectacles only see colored objects, doesn't see shapes at all. And the other just see shapes, but doesn't see colors. So this is like a measurement, if you like. The looking is like a measurement. And you say, okay, the color spectacles correspond to the operator C, find a color, operator S, find a shape. And in this quantum world, we have a non-commutation relation between shape and color, just like the non-commutation relation between position and momentum in quantum mechanics. Okay, so now what you do is you put your glasses on and you pick out a set of red balls, a color red. Now, how do you distinguish, how do you talk about these balls? Because we can't call them red spheres because you're not allowed to do that in quantum mechanics. So we say we describe the red balls by this symbol, psi r, or the symbol psi sub b, and these are just the eigenvalues. They're the German name for it. So the eigenvalues, these are the eigenoperators. This should be function, by the way. No. Yeah, sorry, these are the eigenvalues. Sorry, I'm not reading this properly. The eigenvalues are red and blue. The eigenfunctions are these symbols here. Okay, so what you do is, as you put your color glasses on, you pick out all the reds, and you've got a pile of reds. And then what you do is you put the shape glasses on, and you pick out the spheres. Okay, so you've got your red ball. Come on, you can play cricket now. It doesn't matter if they hit them in the next door garden because you don't have to go and get it. You've got another one to play with. And then someone says, but wait a minute. Are you sure they're spheres? So you put back on your color spectacles just to check, and you find half of them have turned into cubes. That's quantum mechanics. So somehow your looking is disturbing or affecting the system in some way. Okay, why is that? Well, that's because if you find psi r, you can always express the wave function psi r in terms of this linear combination. And that is always S and C, sphere and cube. But we always find sphere or cube. So although we find some way of objectively reducing the wave function, collapsing the wave function, doing something to it, you're not free of the problem. Because if you now look at that wave function you've collapsed, oh my goodness, it's suddenly got a linear combination of red and blue. And this is the infamous measurement problem. And this measurement problem will never be solved because it's the wrong question. Okay, but before I get really entangled about that, hot under the collar about that, let me have a look. We could probably get away with, no, we can't get away with it local, but let's have a look what happens when it's non-local. And this is where we come to entanglement. So the wave function of these two particles, when we've got them in this entangled state, can be written in two ways. A linear combination red, blue, blue, red, or a linear combination sphere, cube, cube, sphere. And this just transforms into this. They're the identical state. They're not different states. They're just expressed differently. And the way to think about it is that each state is implicate. When you're thinking about this state, you're just looking at that as being the other state is, as it were, enfolded into the background in some way. So I'm coming to the language of enfolding and unfolding. Okay, so we make the separation of the particles, and then we measure particle 1, and we find that the particle 1 is R. Okay, remember we're doing this on Earth, and then if the other particle is on the moon, it must be 2. Because it's quantum mechanics says it must be 2. You've collapsed the wave function to this, if you like. And here's the collapse coming in again. But the shape measurement on 1, then you find the shape. And therefore 2 must be 2. But you haven't touched particle 2. And therefore it looks as if particle 2 is in a state which is not allowed in quantum mechanics. It cannot be simultaneously in an eigenstate of shape operator and color operator. That was Einstein's argument. But so once again, simultaneously it's B and C, not B or C, which is demanded by quantum mechanics. So you see, we've got locality rearing its ugly head here. We've learned how in the mathematics to deal with it as an algorithm. And that is what Jonathan and Jose and has already dealt, and Emily touched on it, but they did directly looked at it. So what is going on here? I often think a metaphor is often useful. Whether this metaphor is useful or not, you're going to get it. This is the Gestalt, to do with perception. So is a quantum measurement something more like a perception? If you look at this picture, and here comes my stale joke, so I apologize to people who've heard it before. It's a picture of a young lady and an old lady. And you have to oscillate backwards and forwards to see it. I see the old lady, and I've often wondered whether that was a problem for me. Where I really would like to see the young lady. Come on, BJ, grow up. Well, the young lady is looking in that direction, and the old lady's got a nose here, and she's looking down in this direction. You've got the two faces or the vase. And you've got this one, the spotted dog. I don't know whether you can see him. I can just make him out in that set of blobs there. Takes a bit of time. And then, of course, a bit of humor, the futile argument of whether it's 6 or 9. Okay. Now, let me go back again. So let's have a look at what Bohr wrote. Remember what Bohr wrote said it was the influence on the very conditions. What is its influence? Get a clue if you read clearly, read some of Bohr's literature, and he introduces the idea of wholeness. So notice it's Bohr who's introducing the idea of wholeness. Sometimes when I am amongst the Pari people, it's always credited to David Bohm, but it was actually Bohr. And I think David probably got it by Bohr because his 52 book, Quantum Theory, was an attempt to explain Bohr to his students because he couldn't understand Bohr's philosophy when he was teaching it. And what does Bohr say? I advocate the application of the word phenomenon exclusively to refer to the observations obtained under specific circumstances, including an account of the whole experimental arrangement. Now, what do we mean by the whole experimental arrangement? The fact that Bohr influenced quantum mechanics so much, I find very extraordinary. I don't think he'd be given house room amongst today's young physicists. Anyway, let's see if we can see. I had very good fortune of meeting a Dutch physicist, Grunwald. I'm sorry, I don't know his first name. I think it's probably Hans, but he's no longer with us, unfortunately. And in 1947, he actually wrote some very, very interesting papers about quantum mechanics. They're neglected, sadly, in the present day literature. But he left me with this box, and I don't know whether this box is where it is in the literature, but it's a box that I made a drawing of for those days of overhead transparencies where you can control what is going on rather than the computers stuff that we have nowadays that us old men don't know how to handle. I'm sorry. So what we've got here is a half silvered mirror. Photon comes in, path length, and then we can produce fringes here. The other photon comes in this way, fringes. But now, experimental apparatus, is it interfering or is it doing something more serious? Well, if we keep that nurdled nut, you see, it's a nut which we can change the path length of this path here. So if we change that path length, we change the phase that the particle arrives here, and so we can move the fringes. So here, if we keep that fixed, we get fringes. But if somebody comes in and changes it while you're not looking every so often and randomizes it, you won't see any interference pattern here. You'll see the classical result. So that's the way you can think about how the experimental arrangement doesn't tell you what mechanism there is. There isn't a mechanism here. There's something else going on. Okay, let's see if we can get a little bit closer. The standard approach, which has been explained to some of the group here, a whole of the group, I hope, introduced the bracket language, and Jonathan, I think, explained it very nicely. But it's a bit of a mystery. It's always been a mystery to me as well. But suppose we think of mathematics as a language. And we need a language, we need a written language. Now, our language, at least the Western language that I'm very familiar with, is process essentially described by verbs and objects by nouns. So you have the noun raining, and you have the noun rain, and you have the verb raining. So in mathematics, you have numbers which you can think of as nouns. So 2 is a noun, 3 is a noun, but what is the verb? Well, the verb can be thought of as multiplication in the sense that you've got 2 possibilities. You double 3 or you triple 2. And therefore, you can write that as 2 cross in brackets 3 or 2 cross with the cross the other side, 3. And in this case, we all know that that's always equal to 6. It doesn't matter whether you take 2 times 3 or 3 times 2. So the mathematical language that we have been brought up to talk in is a commutative language. Physical processes, on the other hand, are about energy flowing from, say, a point P to a point P2. And I haven't defined what a point is yet even. Some region P1 to some region P2. And I can actually use this empty. That's interesting. What does this empty one mean if we've got it moving in this direction? Well, we're thinking about the movement of energy from point to point. So suppose we have I've talked about this, a process called translation. So then we can say, all right, let me put it in here. That's the symbol for translation from P1 to P2. And I put it inside the strange symbols. But I can pull the strange symbol out and say, we're going to translate a distance D. Or we can say, my translation already has D built into it, and I'm acting on what? Let me do the same for the rotation. I'm then rotating on, but what is this? Well, it's like a placeholder. it's telling you something about the system that is absolutely vital. Placeholder, why am I using the word placeholder? Because the 0 was always thought historically as a placeholder, a hole in the sand. And here is my placeholders. They exist as actual entities. And I then put my marbles in. It's a game of some kind I got off the internet. And if we think of the marbles as the nouns, then this is the placeholder for the noun, which is the eigenvalue, whereas the operator is the related to the eigenfunction. So what we have is the arrow is a becoming, P2 becoming, a P1 becoming P2, whatever those are, symbols are. But then we've also got being, because if we make P2 equal to P1, well, that's not the right diagram for it. That's the right diagram for it. And so being is the identity, and the mathematicians call it the idempotent. And I thought I'd introduced this story. I've discovered it in Dirac. I discovered so many things that I think I've understood myself, created myself, and found it's ruddy Dirac got there first. And quite rightly, because he actually invented this notation. And he said, in order to try to understand quantum mechanics, we need to invent a mathematical language. And he invented this mathematical language. And this object here, for the people who know about Dirac, is called the standard ket, not the ket, the standard ket. It's in his textbook. Long story about it, but most people ignore it. In the, what is it called? Principles of Quantum Mechanics, a classic book that we probably all us physicists have got to read if we're going to do quantum mechanics. So there's the standard bra there. If you put a number in there, it becomes a ket, not a standard ket or a standard bra. Okay, and so here's the activity. P1 to P2 is actually the activity which goes from here to P3. That's a rotation taking me from P2 to P3. How do I put them together? Okay, how are we doing for time? Okay.
Almost half past.
Almost half past. When can I go on a bit more?
Yeah, go on.
Because this is the vital new part of the whole thing. Now then, we've introduced this magic imaginary number, we call it. And it's magic because I squared gives you -1. Well, Clifford said, don't treat it as a number, treat it as a rotation. Treat it as part of your explanation of how to get to the George. Turn right at certain junction, turn left. So it's really a rotation. So let's symbolically write the I as a rotation. So that means that if you start with up, rotate it through 90 degrees, you're going right. So when you're going up, turn through 90 degrees and you'll be going right. Okay. Do it again. Right, right. And what are you doing? Here it is. Go right again. Well, you're going in the opposite direction. So that's where the negative sign comes in, because these are arrows pointing in the other direction. And the negative is when you put the arrow on the other side. So what we've got here is the P1 and P2. The mathematicians never miss a trick. P1 is called the source of the movement, and P2 is the target. And for anybody who wants to show off, this mathematical topic is groupoids. We don't need that. We can do it just by thinking about it. Okay, so now we really need two placeholders. a before noun and an after noun. And so we actually divide this into two, P1, P2. And this is just related to the density matrix, and it's what the physicists call a transition amplitude. It's the probability of going from 1 to 2. So once you master this language, you're essentially doing quantum mechanics. And I want to draw your attention to the fact that it's not just me that's crazy. Bob Koch, absolute magnificent guy, Oxford University in the computer science department, published a paper, Kindergarten Quantum Mechanics, based on what I am telling you now. Okay, so the official language behind quantum mechanics that I work with, groupoids, and they can be generalized into orthogonal and symplectic Clifford algebras. That's just for the record. Don't have to know that at all. Now, folding and unfolding. Just want to get to this part and we'll finish. The time translation is, it's just like Huygens. Schrödinger's equation is just Huygens construction with no messing around. And that's Feynman. Feynman says that. So you take each point and you fold it into the wave function here. So you take that wave function, all points along here, do a transformation on each one, and the sum of all these contributions will then give you what is happening at this point. But then what you want is to have something to do with what's called the bra. This is to do with the ket. We've got to get the bra in there, and it's called a conjugate wave function. It's a complex conjugate. And that is information coming from the future. That's not me. That is written by Feynman in his paper. It was in his PhD thesis. So this is information coming back. But then what David said was, no. This is enfolding and this is unfolding. So you're showing what motions will give rise to not just a point, but a whole series of structures. So you're really, what you're talking about is you're transforming a structure at P1 into a structure at P2. And here I'm using multiplication in the Leibniz sense that it's the order of succession. Whereas addition is the order of coexistence. And that's why the coexistence, why I was writing 1 and 2 rather than 1 or 2 earlier on. And this is known as a twisted multiplication. But no, we don't need mathematics. We can do metaphors. You see, physics, in classical physics, if you understand dynamics, it's always about trajectories in phase space. But in quantum mechanics, you can't do that. So you've got to have this folding and unfolding. And then David Bohm was watching television one day, and he saw this remarkable diagram illustrated on the television. You can find it on YouTube. You've got 2 cylinders, plastic cylinders, and you've got a glycerine here. And it's a rotation. So you get hold of this and you wind it so that you are stirring up the liquid. Put in 1 drop. Then after n turns clockwise, you find no drops at all. You just have a uniform color, slight coloring of the liquid. Turn it back again, and you find the dot returns. So here you have the idea of an implicate order, that the order of this drop is already in there, although you can't see the damn thing. but you can unwind it and it becomes. So you can think about a process of folding, unfolding, that what is actually happening is not that the energy is following a trajectory, but you can make a trajectory out of a mean number of foldings and unfoldings. So it's really the continuity of substance, not the continuity, sorry, the continuity of form, not the continuity of substance. So that begins to move us definitely away from a particle moving there. It doesn't move us away from energy, provided the energy puts some form into the whole process. And then we can quickly show, and I won't go through this, but if you fold and unfold, you can get an equation which looks like the Heisenberg equation. And then when you split it apart by writing the explicate order in terms of a pair of bras and kets, you actually find two Schrödinger equations, one working one way, the other one working the no way. And here again, I thought I had got the unique solution here, but in fact, I then found it was already in Dirac, 1930, before I even came on the scene. Okay. So the point is that when people are talking about quantum mechanics, they present you with the Schrödinger equation without explaining where it comes from. And everybody accepts it because it works. But is it telling us something about reality, or has it hidden reality behind it and supplied us with an algorithm? Bohr certainly called it an algorithm. And Schrödinger wasn't quite clear. He wanted to make it into something more physical. But if you try and find out where the Schrödinger comes from, it comes from this idea of activity, of folding, of enfolding. And it's very dramatic. And I'd like to just finish. I've got one more slide and then I'll call it a halt. Okay, James? Because I think this is very important. Let E, and I'm getting this from Eddington, let E be the operator for existence, satisfying exist times exist is, you hope, still existence. Okay, so then the eigenvalues are either 0 or 1, and this is Boolean logic. And this is the logic. This is why you keep telling us quantum physicists, you're being illogical, because you're actually using Boolean logic, assuming that Boolean logic is universal. But when you've got a non-commutative structure, these operators of existence might not commute with each other. So you can say either the eigenvalue exists or you don't exist, A, or B exists or it doesn't exist, but you cannot talk about the existence of B if you're talking about the existence of A. Boolean logic fails, and that's why the Cartesian order fails. And that's why I made some comments in Emily's talk, because she was trying to fit everything in to a Boolean logic situation. Whereas in fact, what we should be worrying about is the implicate order, the non-Boolean logic. And David's implicate explicate order is a non-Boolean logic. It's about B being enfolded into A or A being enfolded into B, a bit like origami. Or in fact, what struck me even in Emily's talk was she used the idea of Sudoku. Now, it wasn't that Sudoku had to have that in, but the process, the board Sudoku was traveling in time. And once you put one element in, or one or two, I don't know how many of the minimum, you are now fixed on what has to go next. So it's not a question of anything traveling, signaling. It's a question of satisfying a certain structural rule. So you're looking at structures transforming into structures. And so we've got to look much more closely at the mathematical structure theory. And so what you've got, just to summarize the idea, the overarching structure is that you've got a commutative, non-commutative algebraic structure, which gives rise to these two shadow manifolds in the example I've given, but they come from process, activity, and David and I wrote a paper on, introduced the idea of the hollow movement, and the hollow movement is the implicate order from which you explicate the shadow manifolds. So I think I'll stop there. David, if that, sorry, James, if that's okay.
Yeah, of course, not a problem. Thank you so much, Basil, for showing us your work and your entanglement with entanglement. I just wanted to invite Jonathan in to see if he had anything to comment, add, or ask.
Well, a couple of points I was going to raise with Basil, if he wouldn't mind. One is just taking you back to the quantum potential again.
Yeah.
I'm
sorry, I'm interrupting again. I'll say, oh, sorry, Jonathan.
Quantum potential energy. You've shown how it acts as a background, if I can use that phrase, for how entanglement might be explained, how these correlations might be explained. And
Jonathan, it's not a background. It is the process. We've got to get away from thinking about a background. There is no background. The background and the foreground are one in a. Okay, sorry.
No. I accept that scolding. That's a very fair point. The question I was going to ask is, you brought it into relativity, and I just wondered what it, if anything, it has to say about the exclusion principle.
Yes, yeah. Oh, but that's a long story, Jonathan. That's another story.
Sorry, but
yeah. The point being that we can move the activity. You see, when you think about what I'm trying to get across is there's no distinction between the noun and the verb in the language that quantum mechanics is using.
Yeah.
Because you've got that empty container, you see.
Yeah.
So the whole thing is active. Now then, what you've got to have is a process in which the activity is, how can I explain this? I haven't set up enough formalism for it. The point being that, let me try another way. Let me try another way. One of the things that we deal with, and I'm talking mainly to Jonathan, so I hope other people don't mind, we have irreducible representations, okay?
Yep.
And a lot of the work I've been doing is based on irreducible representations. But what's the most fundamental irreducible representation? It's the representation which makes things either symmetric or anti-symmetric.
Okay.
And if you read Weil's book, now wait a minute, which one is it? It's either his space-time matter. I think it's his space-time matter. And what he says is that once you insist on making exchange irreducible, symmetry irreducible, you're stuck with what he called the Mike-Ike problem. In other words, you can get a long way with Ike and Mike being separate entities until you put them in a symmetric state or an anti-symmetric state. And when they're in an anti-symmetric state, then you have the Pauli exclusion principle working.
Yeah.
And it's there that it goes in. It goes in the algebra itself, not in the wave functions. Have I got across what I'm trying to say?
I think so. I think I've got it. Yeah, I think I've got it.
You pull the operators out and make them anti-symmetric.
Yeah.
So the whole movement is an anti-symmetric move, whatever that means.
Yeah. Yeah. Well, I hesitate to ask my second question because it could be an even longer. You said this could be a long story. This could be an even longer one. I don't want to put you to the trouble, but you kind of tiptoed around the measurement problem by saying you're asking the wrong question. Can I at least ask what the right question is then?
The right question is to try to understand this unfolding movement and what its consequences are.
Okay.
Part of the weak value measurements that we were doing was a way of trying to get around this. Now, I've moved quite away from the original Aronoff and Weidmann introduction of this subject. But the essential point is you want to make interventions which do not change the wave function, that do not collapse the wave function.
Yeah.
And these are weak measurements. So you just tickle the system. Okay. And what you find is that the output is very interesting. You have a lot of oscillations coming in. We are getting extraordinary results, which we're trying to make sense of in the experiments we're doing. So if you insist all the time, make a measurement, collapse the wave function, you're not going to see these more subtle features, which will be exposed, which will expose whether this activity really, this process idea is really giving us something useful again.
Okay. Okay,
and
thank you.
I think it's quite remarkable that the kind of results you get. But again, it is a long story, but people ought to be aware that it is being told in other circles.
Right. James, throw it open to anybody else.
Yes, let's do it. I'm just going to stop your screen share, Basil, for you.
Yeah, sure.
So so to open it up, the standard guidelines apply. You can use the raise your hand function under reactions at the bottom of your screen, or write your question in the chat and I can read it out for you. I can see Richard has his hand up.
Thank you, James. Again, this is from a non-scientist who has difficulty in following the mathematics. I just wanted to come in, if I may, on firstly a quibble and then a question. The quibble is linguistic, that the ing form in English, as you mentioned in raining, is not just a verb, it's part of a verb. It's a participle when it's part of a verb. And it can be a noun as a gerund, and it can also be an adjective. So I think rather than noun and verb, it might be better to say state and process, because the linguistic analogy doesn't quite work there. You know, in other words, the ing form can include the non-ing form. Raining can include rain. That was a quibble. But the question was, I'm a poet, and I think as a poet, one of the keys to poetry is metaphor. And I'm just wondering if you would accept the idea that metaphor itself is linguistic entanglement.
Yes, I think. First of all, thank you for correcting. I knew when I was going through this, there's going to be someone in the audience that's pointing out that I'm being too simplistic. The reason why I don't use process and state is because that has a meaning in physics which is not the meaning you would like to give it because you're a poet. Therefore, I have to try and get away from that idea. Now, metaphor. Metaphor is because we are pulling out of that features that you want to emphasize, but there are also other features which may be getting in the way. Is that the sense you use the word? They might be entangled. It might be an example of entanglement, the metaphor. The metaphor itself is entangled.
Well, I'm thinking, for example, of, let's say, two discrete systems, or you could have three discrete systems of literal language. You could say, for example, king relates to people, or ruler relates to citizens, and everybody knows that you're talking about a literal hierarchy. But if you then move that idea into the zone of creatures, mammals, you would have, let's say, lion and animal, or eagle and bird, or head and body. Now, you've got four different systems there, which are totally literal, hierarchical systems linguistically. But supposing you start fooling around with them and you mix them up, you get statements like, the king is the lion of his people.
Mm-hmm.
David is the Lion of Judah in the Bible. The king is the head. The king is the head of the body of the population, and so on. So you've got different systems.
Yep. No, I wholeheartedly agree with you. But why I'm using these metaphors is I'm hoping I can give some insight into the mathematics, because as you say, you don't really get the feeling for mathematics. Now, it's the whole point I'm trying to make is the feelings are put into mathematical form and they have a certain grammar. And it's the grammar that I'm trying to get across by example. When I grew up in India, I could speak Hindustani fairly well. But to actually analyze it into terms of subject, verb, and so on, I wouldn't have a clue. Because what I was really doing was just being able to communicate with sounds. And as long as those sounds got me what I wanted, usually as a kid, you're selfish, what I wanted, then that was good enough for me at that stage. And I think it stayed with me. And the mathematics is very much like that, except of course you've got to work harder, just as you have to work harder with analyzing the structure of language.
Yes. Thank you very much. Fascinating. Thank you.
Thank you, Richard, for coming in. Always great to hear from you. And next, I'd like to invite gentleman from Fetzer. I believe is it Tim Eastman?
Yes, this is Tim Eastman. Asking a question. Can you hear me?
We can, yes.
Yes, hello, Tim.
Thank you very much. Very excellent and clear presentation, and I learned so much since I had previously read your Undivided Universe, and there are a number of questions that raised in my mind, especially after being exposed to Hans Primus's excellent work, Knowledge and Time, which in his first few chapters, he articulated so well the distinction of the Boolean and non-Boolean description, which wasn't really brought out in your Undivided Universe work some time ago. But I'm so pleased to see that you made such a clear discussion of it now. So it strikes me that your interpretation, say the possibilist interpretation of Ruth Kastner, the possibilist interpretation of Epperson and Zafiris, these approaches are very robust in understanding quantum phenomena without having to go to the many world interpretation and multiverses, which appear to be just presuming Boolean only logic for the fundamental logic and actualism, and then getting into what it seems to me ontological overflow, and that it's much more simple to be, as you're describing it, to try to isolate the essentials of the quantum physics in a way that can be more consistent with our understanding of both process and interrelationships in the real world as we encounter it. Any comment?
Yeah, no, that's quite right. I mean, I've had many a conversation with Hans Primus when he was alive. And in fact, I was introduced to him very early on in my career, and I found a mimeographed, I've still got it here actually, but it's so important. So I don't know why I want to get it down, just to show you that it was this, in which it's called quantum mechanical systems theory. And that is that was published in 1978. That's when it was published, but I got the book long before 70. I got it in the early 70s, and I was absolutely fascinated with his work because he's a quantum chemist and comes in from the chemical angle. And I think we physicists sort of have not taken chemistry seriously enough. We think it's just an application of quantum mechanics, but it's not. It's a very interesting subject in itself. And Hans and I often talked about this. And I at first I wondered why he was interested in what I was saying. And then I suddenly realized that we were actually talking the same language.
Oh, yes. Well,
but first, and then there's a second part to your question was, why wasn't this in the Undivided Universe? It wasn't in the Undivided Universe because this is something which I have actually put together since David left us. And this is the work, thanks to your institute, that has inspired me to think about these things. Dropping helium atoms is not as easy as it sounds. And the problems that we had to face there certainly made me think very deeply about what is going on.
Oh yes, very good. Oh, by the way, I'm a space physicist myself, not a quantum physicist, and it's my wife who has a connection with the Fetzer Institute as a board member with Fetzer, but I appreciate the acknowledgement of Fetzer's contribution to helping to encourage discussion.
Yeah, please hand on my thanks. Many, many, many thanks.
Thank you.
Thank you, Tim, and thank you for joining us today. Next, I'd like to invite Jorge, who we haven't heard from yet in this series.
Yeah, thank you. Can you hear me?
We can, yes.
Yeah, well, thank you so much, Basil, for your inspiring talk. I have two questions or remarks. First, regarding entanglement, could you eventually calculate that if you didn't have entanglement, then our macroscopic world would break down or break apart?
Oh, very, very much so, because the entanglement, as I indicated in my talk, is the raison d'etre for the covalent bonding in chemistry. And that is one of the strongest bonds that we have. But also, I had experience in ferromagnetism using the Ising model. And although that's a classical thing, the actual force between the neighboring atoms, in that case, is quantum mechanical in origin. We have no rigidity in relativity, for example. And the rigidity comes from the quantum theory. And that's why I don't think we've brought together the full implications of relativistic quantum mechanics. There's a lot more deeper connections there, which Hans Primus certainly brought out. Does that help?
Yeah, thank you. And second, thank you so much. So the second question regarding the analogy between a metaphor and entanglement. It seems to me that metaphor also has an important poietic role, as in autopoietic systems. In some sense, you hallucinate seeing something else when you look at something in the sense of Seth. And so in this sense, you eventually metaphorize something which is not there, which is not yet an object. Do you see this aspect in entanglement? Or do you think
no, because my understanding of entanglement comes from the actual mathematical structure. You see, this is, and I've always complained that I have great difficulty in explaining in general terms what is in the mathematics, because there's a lot of very subtle features there, which unless you have actually been through the details, you don't see the essential features. And I don't know what to do about it. I mean, I don't think anybody knows what to do about it. We just have to try to filter out a way of talking about it so that we catch the essential features of the mathematics. I'm sorry, that's my problem. I've always said, and that's why it's a standing joke. Oh goodness, why can't Basil Hiley talk without putting a mathematical equation on the screen? Particularly from the Pari collection of people. And I try to get the intuition behind it. And that's really what my talk was about, providing some intuition so you're not left out in the dark.
No, but I think that you really succeeded quite well. Yeah.
Thank you.
Thank you so much. Yeah.
Thank you.
Thank you, Jorge. Just to clarify, we do like some math, but we just don't understand the language. Next, are you happy to take one more question? I know we're approaching the top of the hour, but are you happy, Basil, with one more?
Yes, yeah. I'm having a meal with my daughter this evening. She hasn't appeared yet. She's going to do the cooking. It's not my turn to do the cooking today.
So let's take one question. Someone else who we haven't heard from yet, Zoe.
I think you're muted at the moment.
I just wanted to say thank you for your beautiful presentation. Your work really touched my heart. I find it fascinating. Thank you so much.
Oh, thank you. I'm glad that the cock up about the presentation didn't spoil things for you.
No, not at all.
Good. Anyway, by the way, are you a scientist or a poet?
No, I'm a poet.
Okay, good. No, I'm trying to say that mathematics is really poetry.
It is. It is.
But I can't get it across, because people still think, oh my God, as soon as I see an equation, and I wish it wasn't that way.
I think it looks just like poetry.
Yep, good.
Thank you, Zoe, for coming in and showing your appreciation. So as we are on top of the hour now, just like to come back to you, Basil, see if you have any final words to leave us with today.
Well, my main hope is that I've actually conveyed some energy into actually thinking along these lines in quantum theory and elsewhere, and trying to connect them up with more general ideas. I'm an old man now, and I'm fed up with people telling me that the question is the measurement problem in quantum mechanics. I say, no, it's the wrong question. And we have to learn exactly why it's the wrong question. And it's the wrong question because we're looking at things organized in a mechanical way still, although we're saying it's non-mechanical. We're not really understanding fully what a mechanism is. and and where, I mean, this idea of using process, of course, has a history with Whitehead and a few others. David Finkelstein was very much in favor of using the process idea, but it's difficult. It's difficult. The concepts still are not there. But I've noticed recently that in computer science, particularly in Bob Koch's work in Oxford and Samson Abramovich, who I hear is now in the University College London, he has some extremely interesting papers, which I have just discovered. You know, we have an internet with too much information on there, and there has to be a way of trying to deal with that information and get the right information to the right person. And I see it's moving in that direction. We're using mathematics to analyze language. I mean, maybe we don't like that, but that is what is happening. And I hope it's not just to compute, make everything into algorithms. If it's making everything into algorithms, scream, I want to get off the planet, because I've had enough of algorithms. I want to understand what it is that's going on in terms that a human being can understand. So I'm just encouraging the youngsters, please take up the baton and continue searching for poesis.
Absolutely. Well, thank you, Basil. I mean, it's always great to hear from you, and, you know, about providing the energy. You have enough energy for everyone. So I'm sure you have inspired people, definitely here. And I know I've heard you speak many times, but it's always inspiring to hear you speak.
Thank you, James. Thank you.
Thank you.
I don't do it deliberately. It's just me. You realize that it's me.
Yeah. Absolutely. Yeah. I mean, actually, that's something else I noticed, that you can't talk about physics without tying it in with your life. And it's really refreshing to hear, to feel that passion coming through when you speak.
Oh, I hope it helps.
Yeah. So thank you anyway. And thank you everyone who has joined us today with your comments, contributions, whether on camera or on the chat. Before we go, I'd just like to invite you all to next week's sessions for this series, where on Saturday we will have Dr. Dean Radin talking to us about entangled minds and matter. And on Sunday, we will have Dr. Vandana Shiva talking to us about living in a non-local world, entanglement meets ecology. So I hope to see you all then. Also with that, not necessarily part of this series, but part of our Power Center events, on Wednesday, we will have the next installment of the Future Human series, hosted by Alex Gomez-Marin, our president here at the Power Center, who will be in conversation with Kumar. So should be a good session, so I hope to see you then. Until then, please contact us on our website or on email. Eleanor@powercenter.com is the best place to email. But yeah. Thank you again. Thank you, Basil, and we'll see you again soon here at the Power Center. Bye-bye.
Thank you for inviting me, and thank you all for listening.